Okay, this is Module 2, where we'll do some problem solving involving, at the beginning, osmosis, and then we'll look back and do general problem solving in Study Guide 17 on diffusion problems. Okay, so our first example here, we have a red blood cell in sodium chloride, and the red blood cell has an osmolarity of 0.3, okay? So that means that there's your red blood cell, and it has a 0.3 osmolarity, okay? And this is meaning that there is some solute inside the cell with a 0.3 osmolarity, and it's placed in a 0.12 molar sodium chloride solution, and the whole thing's done at 20 degrees Celsius, okay? And so the first part of the question asks, what is the percent volume change does the cell undergo, if any? And the second part of the question asks, if the cell initially had an osmotic pressure of 3 atmospheres, what is the osmotic pressure after swelling? Okay, so like what happens here? Well, remember that a 0.12 molar sodium chloride solution corresponds to 0.12 molar sodium and 0.12 molar chloride, and that corresponds to a 0.24 osmolar solution of sodium chloride, okay? And then you have this cell, which I'll just repeat here, at 0.3 osmolar of some solute in the cell, okay? Now, the membrane here is semi-permeable. So the membrane here is semi-permeable, and what that means is that the sodium chloride doesn't pass through the membrane, okay? However, water can pass through the membrane, and water will pass from the region of high concentration to low concentration. And in the region where you have less solute, the 0.24 osmolar, this is a high water concentration because it's a low solute concentration, and this is a relatively low water concentration. And so the water will flow into the cell, and as a result, the cell will swell. So I know that the volume will go up and the cell will swell, okay, because the outer solution has a lower osmolarity than the liquid inside the red blood cell, okay? So then the question is, how much does it swell by? And so, well, it will swell until there is no more driving force to swell. And so outside here, I have a 0.24 molar, osmolar, sodium chloride solution. And inside I have a 0.3 osmolar solution. And water will flow inside. Now, the assumption, though, is that the solution is rather large compared to the amount of water that's actually flowing from the solution into the cell. And so the flow of water from the solution into the cell doesn't actually change the concentration outside the cell. So this is fixed, even as the water flows into the cell. And so what happens is the 0.3 osmolar, this, inside the cell, drops until it reaches the 0.2 osmolar outside. And then when the osmolarities inside and outside the cell are the same, the water flow stops, okay? And so you can calculate then the volume change from just this change in osmolarity, because the osmolarity is the number of moles per unit volume. And so therefore initially, right, you have the sort of moles of solute or osmoles of solute divided by the initial volume is equal to 0.3. And then finally, you have the same number of osmoles of solute divided by the final volume is equal to 0.24. And as I said, the osmoles of solute inside the cell don't change, they're there. And so if you take a ratio of this divided by this, you'll get an expression for VF divided by VI, which is just 0.3 divided by 0.24, okay? And that works out to a 1.25. So VF is 1.25 times VI, or this works out to a 25% increase in the cell volume as it swells, okay? And the second part of the question asks, if the cell initially had an osmotic pressure of 3 atmospheres, what is the osmotic pressure after swelling? And so this is actually a problem where you look at the initial osmotic pressure and you look at the final osmotic pressure. So the initial osmotic pressure is given by RT times the initial concentration inside the cell, which is 0.3 osmoles per liter, okay? And you can multiply by 1,000 liters per cubic meter if you like. And then the final osmotic pressure is given by R times T. That doesn't change, but you have a final concentration of solute, because your volume has gone up, of 0.24 osmoles per liter. Again, multiplying by 1,000 liters per cubic meter. And then all you have to do is divide the final osmotic pressure by the initial osmotic pressure and use ratios to solve this problem, okay? The RTs will cancel and you'll just get 0.24 over 0.3, okay? Which means that the final osmotic pressure is then 0.24 divided by 0.3 times 3 atmospheres. And that works out to 2.4 atmospheres, okay? And so because the red blood cell has actually swelled, the pressure inside the cell actually decreases to 2.4 atmospheres. All right. Let's do a similar problem here. You have a isotonic sodium chloride solution, and you have a cell whose membrane is impermeable to sodium and chloride, okay? And then a cell of this type is placed inside another sodium chloride solution, and the cell's volume decreases by 20%. And the question asks, what's the molarity of the second sodium chloride solution? So let's first consider that sodium chloride again dissociates into sodium plus chloride minus, and if this is 0.10 moles, you have 0.1 mole, you have 0.1 mole of sodium and 0.1 mole of chloride for an overall 0.2 osmolar solution of sodium chloride. And this type of solution is isotonic with the contents of the cell. So what that means is that if I draw my cell here, it will not grow or shrink if I put it into this sodium chloride solution. So therefore, its contents must be 0.2 osmolar as well, okay? So I know about the cell. That's the first thing I do is I get some information about the cell because of the information in the first sentence that this solution is isotonic. And then you take this cell and put it into another sodium chloride solution, and the cell's volume decreases by 20%, okay? So that means that the final volume is 80% of the initial volume, all right? And so remember then that that means that okay. Now remember that the number of solutes in the cell is fixed, okay? And so then the final concentration is just this osmoles of solute, which is fixed inside the cell. That's the final concentration, CF, in the cell, divided by the final volume, which is 1 over 0.8 times the number of osmoles of solute in the cell divided by the initial volume. But this is just the initial concentration. So the final concentration is just 1 over 0.8 times the initial concentration. And so that is 0.2 osmolar for CI divided by 0.8, which equals 0.25 osmolar. Okay, so the final concentration then is 0.25 osmolar, and that would be isotonic with a 0.25 osmolar sodium chloride solution. But that is the osmolarity, not the molarity of the second solution. And so I have to convert 0.25 osmolar, okay, of sodium chloride solution is equal to a 0.125 molar sodium chloride solution, okay, because sodium chloride dissociates. So that's the key tricky last step. It's 0.125, and that is B, 0.13. Okay? All right. So let's go back and look at some diffusion problems. Okay, and this is a very interesting random walk problem. So after drinking excessively at the brass taps, your friends blindfold you and leave you in the middle of Johnson Green. And now, so assume that Johnson Green is a big field, okay, on campus, and it has a diameter of 150 meters or a radius of 75 meters, okay? Staggering around randomly, you take 25 minutes to get off the green. So if you start somewhere in the middle of the green and you stagger around randomly on the field, and then you eventually leave after 25 minutes. So this is an example of a drunken random walk. Okay, and it is on a field, which is a two-dimensional plane. Okay, so the fact that it's a flat field means it's 2D problem. And so when I look at the distance I have to travel, which is the RMS displacement for this random walk, I want to use the 2D formula. And I remember that R RMS is the square root of the squared displacement, the mean squared displacement, okay? And in 2D, the mean squared displacement is given by 4 dt. And remember, the 4 is the 2D formula. So I put in root 4 dt in here, and I want to calculate the diffusion coefficient. So I square both sides, and I solve for d. And then I know what the RMS distance traveled is. That's the radius of Johnson Green. So that's 75 meters squared. And I have 4, and I'll put in 25 minutes. So my diffusion constant will end up being in units of meters squared per minute. And I can calculate this out, and this works out to 56 meters squared per minute, which is answer B. Okay, going back even further, in an experiment similar to Perrin's experiments, small particles are suspended in a liquid. And at a height of y1, okay, which equals 1 centimeter, there are 200 particles. I'll call that N1 is equal to 200 particles per unit volume. And then at a height y2, which equals 3 centimeters, N2 at this height is 148 particles, okay? And then the question asks, how many particles per unit volume will there be at some height y3, which is 5 centimeters? So the question is, what is the number of particles per unit volume at that height? And so this problem involves the Perrin's experiment, which you remember depends on the Boltzmann equation. So for example, N2 divided by N1 is equal to e to the minus some constant c times y2 minus y1, where c is some constant. So that's the equation that's relevant to Perrin's experiment. And I don't know what c is, but I'm going to need to figure it out if I want to calculate what N3 is. Now I do know N2 and N1. N2 is 148, N1 is 200. So that is e to the minus c. And then y2 minus y1 is 3 minus 1, which is 2 centimeters. Okay? And then I have to solve for c, but c is up in the exponential. So if I take the logarithm of both sides, I get minus c times 2 centimeters. And then I can solve for c equals minus 1 over 2 centimeters times the log of 148 over 200, which is minus 0.301. And so c works out to be 1506 inverse centimeters. Okay? And then once I have that, I can then use this formula here to solve the more general problem. So I can look at N3, which is what I want, divided by N1 is then e to the minus c times y3 minus y1. Well, remember c now is 0.1506 inverse centimeters. Okay, and so then if I want, I write N3 is equal to N1, which is 100, times e to the minus 0.1506 inverse centimeters. And then y3 minus y1 is 5 minus 1, which is 4 centimeters. So the centimeters cancel. And I get N3 is 100 times e to this, and e to that works out to be 200. E to the e to the negative 0.1506 times 4 works out to be 0.5476, and this works out to be 110 particles. Okay. An alternate way of figuring this out is to realize that y5 minus y3 is 2 centimeters, and y3 minus y1 is also 2 centimeters. And so the formula for those numbers, y3 minus y2 and y2 minus y1, yeah. Okay, and so then I then get that N3 divided by N2 satisfies the same formula as N2 divided by N1, and so N3 is equal to N2 squared over N1, which is 148 squared over 200, and again that works out to about 110. Okay, so that's another way of doing it, an alternate route to the solution here. Okay. And oh yes, 110, the answer is D then. Okay, one final problem here. If the flux of molecules diffusing through an area of 1 square micron on a cell membrane is J1, okay, so there's 1 square micron, 1 micron by 1 micron, and I have some particles moving through it like this, and a flux J1 through a cell membrane. Then the flux of molecules diffusing through an area of 2 square microns is, and you're given several options. So 2 square microns, well, it's a bigger area. Okay, there is your 1 square micron. That's what you had before with your particles diffusing through it. And now you've expanded the lengths by √2. So this is √2 microns by √2 microns to give you 2 square microns area. And so the area is larger, but not only is the area larger, but the particle flux is larger, because now you're getting particle flux through this this part here. Not particle, but the number of particles passing through is larger. So you get two things. The area is going to twice the area, but the number of particles passing through also goes to 2 times the number of particles, because you have 2 times the area of opening. Okay, and this number of particles passing through is what we call delta n, and you look on the sheet look on the formula sheet for the definition of the flux, which is J times 1 over the area times delta n per unit delta t. Delta t doesn't change, but both the area and the number of particles passing through the area are increasing by a factor of 2. And so let's call this J2 is equal to 2 area and 2 delta n delta t. And the 2's, so there's a 2 in the denominator and a 2 in the numerator, because twice as many particles are going through twice the area. But you see then that this is just then J1. And so the J2 is equal to J2, the total passing through this, the total flux through this is equal to J1. And so the answer is E. Okay, thank you.